Good evening and welcome everybody. It's Obi-Wan PS4 and Simplex Pachinko. We are doing some GRE tonight. So, looking through cracking the GRE math subject test by the Princeton Review, 2nd edition, copyright 2002. So, for the most part, this is how we operate with our Wednesday night math calculation type streams. If anybody has any particular questions that are not, relevant to GRE, that is perfectly fine. I'm just basically going through the GRE questions to try and to give us some inspiration as far as what to work on while we're waiting for other people to ask questions. So again, if you have any particular questions, feel free to ask them in the chat. And those of you who are on YouTube, hi YouTube, come on over to Twitch at some point, or you can, in fact, well, don't ask anything time sensitive on YouTube, but if you have any particular questions and maybe I'll get to it at some point, I can answer something there. I hope you all are having a lovely week so far. We are, right, this is Wednesday. One of my friends asked if our local grocery store had any hot peppers, and I was like, yeah, probably, and I went looking and I found some bird-eye chilies, which are like Thai chili peppers, which have a three pepper hot rating. And then I was like, and I've got these other finger chilies that also have a, hot rating. And then she was like, yeah, those are, more like Asian peppers. I'm looking more for like the Scotch bonnets and habaneros. And I was like, it's really too bad I already bought these. So, those of you who are interested, we are supporting GoTel, that's Game On to End Lupus, for the 2026 campaign season. And I do have some redeems for eating hot peppers. So if anybody's interested, go for it, because I got some fresh ones, as well as the other dried ones, but those are known quantities. They're hot, but at the same time, they're not like... These, I think, are a little scary, because they're just kind of sitting over here and fresh, and I don't know how hot they are. All right, so... And of course, they have the nice little warning on them that says, do not touch without gloves. Yay. All right, let's clear out the... Clear out this old stuff. So we worked on 41, 42. Yep, cool. So we made it through all of the previous page. And now we're going to start working on page 98, which is our second to last. Hey Raven, how's it going? That's not what I want. There we go. So, you're rebranding. Do you have any particular thoughts on what your rebrand shall be? Green. K goes from 1 to n. K over n squared minus k squared over n cubed is going to be what? Okay. So I think for this one, this is what's going to be called a telescoping limit, or a telescoping series. And so, what we want to do here, we will list, oh goodness, simply will not do putting them right on top of each other, but sure, why not? 2/3, 1/2, 1/3, 1/6, and 1/12. Did I eat today? Yes, in fact. I, in fact, had a reasonable amount of food. What is reasonable? I mean, that's a very good question. So this morning, bowl of cereal had to, run out. So not necessarily my optimal breakfast, but, it's fine. And then, let's see, came back home. I was originally planning on going to the library, but they weren't open yet. And so I came home and made coffee instead. Did some of the science work that we're doing on Elite Dangerous, which, yes, is inside of a video game nonetheless, but it's a matter of, testing the testing the programming and seeing what's there. So we're doing stellar density scans of the galaxy. And when I say the galaxy, I mean the galaxy. It's not just the nice habitable regions. It's like as far as you want to go in any particular direction. And then ended up, okay, so you're going to yell, but don't do it yet. So I did skip lunch at 12. Went and did a session of Tai Chi with my instructor. Came back after, had lunch. Now, I grant you, it was like 3 p.m., but nonetheless, which consisted of some leftovers, some fruit, some bread. Yeah, I think that was it. And then well, leftovers. Those do count because we actually have like real leftovers in our house. It's not just like, 5 grams, or it's not like 20 grams of food. It was like an actual meal-size portion. And then went and got my kids after school, came back home, started making dinner, which for us is a kind of an unstuffed chicken pot pie. Instead of being inside of a crust, what we have is like the pot pie stuff, the stuff that goes like in the pie traditionally, which is based mostly of broth, potatoes, mixed veggies, and like some thickening agent. So we'd take some flour, take some broth, and then mix that together, and then dump that in at the end, and it thickens it all up. Ideally, supposedly, this thing should be then dumped into a pie crust and then baked. Who's got time for that? So instead, we just have like biscuits, or as it was in the States, we would take pie crust and like bake the strips of pie crust and then have those as like shovels, so you could dig in, take scoops of that. Never stuffed chicken in the Balkans. Yeah. It's what my spouse's family used to call um, uh, anytime they'd have tortilla chips or dip. No, sorry, tortilla chips or Doritos or stuff like that. They'd just be called shovels. Usually, that would be rather than calling them shovels all the time. It was usually shovels when it was like half stuck in the casserole, in the food, and then you'd like take it out and use that as your use the tortilla chip that was in your food as a utensil. Stellar density is the amount of stars. Yeah, so it's the amount of stars within 20 light years of your position wherever you are. So out in so we'd started in like just outside of Sol, right? It was probably 1,000 light years or so outside of Sol. And so it took like an hour or two to get there. And then once we get there, we would 20 light year radius. So 20 because in Elite Dangerous, the game, your radar thing that's over on the side panel only has a 20 light year range, and so it just won't list anything outside of that. And so it's very convenient because then you don't have to physically count them. Yep. So what we do is we pull up the list on the side panel, and then we look at what is how many systems are there within 20 light years, or if it maxes out at 49 systems in the list, because we're currently at the galactic core, or very close to the galactic core. So it doesn't thin out very much. If you're at the galactic core, or like in a very, very dense region, what you do is you say, okay, this is going to max out at 49 in the list, which is 49 systems plus the one you're in. Right. So 49 systems, and you go all the way to the bottom, and at the bottom of the list, it'll tell you the furthest one that you can reach in that 49. So the system you're in is 0, and then go through the other 49, go to the bottom, and say, okay, the furthest system away for a long time, where we were in certain places, it was 19.9 or 20 light years. So it was like right at the range. And so it'd be like, okay, well, we've got 49 systems within 20 light years. Sounds good to me. Or like 17.3 or 18.7. It gets really close to that. Lately, because we're in the core, our system count is our furthest system is like 8 light years. Which means that there's a lot more stars than that. Like between 8 and 20. It's going to be like 200 or something like that. So they do an extrapolation based on some mathematical formulas that they pulled up in order to I think extrapolate just to get the density of the stars. And you're assuming that it doesn't like just cut off outside of the 8 light year range that I have right now. that maybe it'll fade a little bit or it'll stay at that density at least until 20. And then they figure, okay, here's the stellar density, and then let's plot this on a graph. So typically as we go up and down like this, lately we've been starting at z coordinates of negative 1,000. So 1,000 light years away from where Sol is in the galaxy, straight down. Anti-Zorth, if you will. We go straight down 1,000 light years, or our ship is the carrier is currently well below that. So I'm in a ship that can jump a very long distance in very short amounts of time. So I went from negative 1,200 or whatever up to negative 1,000. Started there, and then started going up through the galaxy until we hit 0, and then until we hit positive 1,000, and then move over from positive 1,000 down to 0, down to negative 1,000, over again. And the coordinates that I'm choosing are basically like just ones that stand out to me for no particular reason at all. Because it's kind of like we want to get something that's sort of random that nobody else is probably going to pick. So I usually jump out a couple hundred light years and then start like working my way this way from our carrier, jump out over to here and then go like that. Just keep doing these basically square waves over and over again until I have a bunch of data, and then come back to the ship, sell all the data, and then the project itself is on documents. So I just upload it via what is that? I don't even remember what system is this in. Yeah, it's just docs. So the forms, yeah. Using forms in docs, I just go through and dump in all of the raw data. So inside of Elite Dangerous, there is a particular mechanism where you go to the Universal Cartographics, which is a company, and they are a bunch of NPCs. They say, oh, well, we'll buy your data. And so when they buy your data, it gets updated to the main server that somebody has noticed all of the following things. And so like the server state is that you discovered a bunch of planets, and they've got my name on the ones that I have discovered. So if I have just scanned the system, you get discovery. If you actually physically go to the planet and then map it, you get another notification or another credit. And then if you set foot on it first, you also get another credit. So you do have to sell your data to the NPCs in order for it to count most of the time. There's some nuances and all that, but we can talk about that when I'm actually playing Elite Dangerous. And then there's also biosignatures. So if you go and update, like go and scan like plants that are on different planets, then you get credit and bonuses for doing that too. So it's pretty cool. Planets are named after people? No. So what they have is a crap ton of systems. And when I say crap ton, I mean like Dr. K. Ross was working at Frontier Developments as their like resident astrophysicist. in order to figure stuff out, in order to figure out how to map the rest of the map, because it was for a while that Elite Dangerous was just a cluster of star systems within a few hundred light years of Sol, and that was it. And like there were fairly limited systems that you could go to, but they all, I think in the original game in 1984, they pretty much all had, cool little systems, or sorry, stations and stuff like that. You could go to all the stations. You could land. You could do trade. You could do combat. But when Elite 2014 came around, they like updated all this stuff. They hired Dr. K. Ross as an astrophysicist to come in and say, I need you to extrapolate the rest of the galaxy based on all of the data. And when I say all of the data, I mean all of the data that astrophysicists had come out with at that point. So like of all of the star catalogs that are on file, we need you to then extrapolate what we think the Milky Way is going to look like on a large scale. And she did. So if you just go to any particular location, yep, no worries. Good luck, have fun. Yeah, the systems are all named after the cataloging system. So if it's an actual catalog, then it lists the catalog and the catalog number. If it's not an actual star system that we know about, if it's just there based on math, then it was named like some particular scheme. So there's millions of systems. It's ridiculous. I love it. Yeah. All right. So, how do we evaluate this limit? Well, we said at the beginning that this is probably going to be a telescoping limit. So what does that mean? Well, try a few terms and you'll figure it out. Right, so when k equals 1, we get the following behavior. 1 over n squared minus 1 squared over n cubed. When k equals 2, we get the following, so plus. This is now 2 over n squared minus 2 squared over n cubed plus, again, k equals 3. Maybe not exactly telescoping. We'll figure it out. I did copy that right? Yeah, okay. So, this is going to be 3 over n squared minus 3 squared over n cubed plus ... So from here, I would prefer to do a little bit of rearrangement and say this is going to be 1 over n squared plus 2 over n squared plus 3 over n squared plus ... And then minus parentheses 1 squared over n cubed plus 2 squared over n cubed plus 3 squared over n cubed plus ... Okay, so not telescoping. The terms don't actually cancel each other out. So my bad there on calling it, but I had thought, maybe. Not so much. That's better. So, what do we do with this? Well, this is just a regular series at this point. This is going to be the summation as I goes from 1 to, is it n? It is n. Well, I mean, we knew this already, but we could have also done this at the previous term and just said that this was going to be two separate. Okay. Okay, so this is as n goes to infinity. So right. This is a little distracting because it feels like it should just be 0. Okay, let's look at this the other way, which is if we look at it in terms of the partial sums, when we change n, right, n equals 1, we're going to get just 1 over 1, so that's 1, minus also 1 over 1, so that's going to be 0. N equals 2 is going to be, we have 1 over 2 squared is going to be 1/4, plus 2 over 4 is going to be 1/2, minus I squared on n cubed, if, right, n is going to be 2, this is going to be over 8. So the first term is 1, and then the second term, n equals 2, is going to get us 4 over 8, so that's 1/2. So it is actually a little bit telescoping, but it's even a bit more different than we were expecting from before. So this is going to be 1/8. N equals 3. Because it's an infinite sum, can at least have some finite value. potentially. So this is going to be 1/9 plus 2, is it just 2/9? Plus 3/9 or 1/3 minus cube is going to be 27ths. Nine 27ths, which is 1/3. So again, these are going to telescope out, and then again, this is going to end up being, this is negative 5 27ths, and plus 3/9 is going to be 9/9. No, sorry, 9 27ths. Should be 4 27ths. Let's just do one more. So this is going to be 1/16 plus 2/16 plus 3/16 plus 4/16, which is going to be 1/4, minus 1/64 minus 4/64 minus 9/64 minus 16/64, which is 1/4. So again, those are gone. Four 64ths is 1/16, so those two are going to also go away. So it's going to be a negative 10 plus 5. Nope, those are 64ths and 16ths. Nice try. Negative 10 64ths, and 5 times 4 is 20 64ths. So 10 64ths, which is 5/32. Not as nice, but the bottom is increasing as the cube. I don't know what the top is increasing as. 1 4 10. Well, anyway. Hmm. So it's going to be the product of k and n minus k. So when n is equal to k, that eliminates. And when n is not k, it's really weird. We could code that up in Python, but that's not the point. I want to be able to just look at this and not have any issues with this. So that's a weird one because, like, most of the time we see the denominator having a variable in it. And in this case, sure, n is a variable, but the point is that it's not the indexing variable on the sum. I don't like this question very much. want to say we could like find a maximum and a minimum for this, but sad. Pick a particular n value, cycle through the k's. Nope, that's not going to work. Right now, this would not be n, this would be the product. Right, whereas this would be discrete, we're not going to argue about that right this second. We could try modeling some of this on Desmos. It's not going to be great, but like, it's worth at least looking at, not just sitting here forever. X times n minus x. Yes, add a slider for n. Then g of x equals f of x over n cubed. Okay. So if we... Okay, so these are the values of the individual terms. So there's always going to be a finite area under this. So we're always going to have a 0 at 0, and then this is going to go off toward infinity. Like, if n is infinity, quote unquote, then like we should just have the straight line y equals 0, in which case there is no area underneath it, but obviously that's not working. A equals integral from 0 to n of g of x. I don't think this is going to work. No, of course not. Why would it? dx. No. Well, there you go. There's our answer. It's a constant. Wow, okay. I don't think I was expecting that. Okay. So now, why is that the case? Parabola with two fixed locations. Well, okay, so if it's a parabola with two fixed locations, 0 and n, how do we work this out? Okay, we can't make the n's come out as if they were constants or something, because that's the endpoints of these. Although, if what's going to work for being definition of integral in this case? They're both times a delta x, which is just going to be 1, unfortunately. if we were allowed to do this, right, from 0 to n, where this is just some kind of constant of x times n minus x over n cubed dx, right? So what is this? This might actually be, I guess this might sort of be the intended way to do it, because as n goes to infinity, our dx, our delta x's being 1 effectively become infinitesimal. So rather than affecting our actual size of delta x, we're affecting the size of the entire thing, which in turn relatively affects the sizes of our delta x's. Maybe. That's, if true, that is wild. Okay, so let's go back to the original formulation of this. It would be from 0 to n, we've got x over n squared minus x squared over n cubed dx. And this is, okay, this is just 1/2 x on n squared from 0 to n minus 1/3 x cubed on n third. Oops, x squared on that one. Half x squared on the first. 1/3 x cubed on the second. Evaluated from 0 to n. So, okay. Oh, yeah. That is, in fact, how this is going to work. It's going to be 1/2 minus 0 minus 1/3 minus 0. So, 1/2 minus 1/3 is 1/6. I mean... That took me a lot longer than I wanted it to. But I think the idea here is recognizing that there is at least something related to integrals. Might not be completely obvious. Certainly wasn't for me. Okay. "44. Which of the following statements are true?" So, statement 1. If a sub n is greater than or equal to 0 for all n, this is, going to be positive integers, but nonetheless. Then sum n goes from 1 to infinity of a sub n converges, implies that the sum of n goes from 1 to infinity of the square root of a sub n converges. Two. If a sub n is greater than or equal to 0 for all n in positive integers, then summation as n goes from 1 to infinity of n a sub n converges implies summation n goes from 1 to infinity of a sub n converges. 3. If a sub n greater than or equal to 0 and a sub n plus 1 is less than or equal to a sub n for all n in positive integers, then summation n goes from 1 to infinity of a sub n squared converges will imply that summation with an alternating term will converge. Okay. All right, if a sub n converges, what does that actually mean? And then will square root of a sub n also converge? So for all a sub n, for all n, a square root, a sub n is greater than or equal to square root of a sub n. Is that necessarily true? No. No. All right, so P series x summation k to the 1.1 converges, summation k to the 1.1 over 2 does not. So, counterexample, this one does not work. All right, ad break starting, so we'll be back in 3 minutes. Thank you everybody for coming, and we shall return very shortly. That's not what I wanted. Come on now. There we go. All right. See you in a couple minutes. Righto. Welcome back. I'm going to do something I'm definitely going to regret later, but I'm going to try one of these finger chilies. Says on it, you have this picture of a pepper, mild, medium, hot, extra hot. It's in the hot section, so, might not be awful. Also says do not handle without gloves, but I'm just going to touch the top of it and go rinse it off. Now, as I said, I am almost certainly going to regret this, but my spouse walked past where these two bags were just sitting on the counter, and she was like, "Why is the air spicy?" Definitely hot. Apart from being very hot, finger chilies aren't really good. They taste basically like green beans or peas. Yeah, just basically tastes like peas. Very boring green vegetable. Okay, so for this, each individual term, n times a sub n, is going to be greater than or equal to a sub n for all of the n values we have, from 1 to infinity. Since the sum of n times a sub n is going to be greater than or equal to the sums of a sub n and going from 1 to z. Sure, why not? All right, for all z. Greater than or equal to 1. All right, all of our individual term values are going to be greater in the n times alpha, a sub n. And also, the partial sums are always going to be, the partial sums are always going to be higher in n times a sub n than they are in just a sub n. So because of that, the sum of a sub n's will also converge. So that works. So the question is, what about 3? So this one's slightly awkward, right? If sum of all a sub n's squared converges, then what does that actually give us? So these are all positive values because all a sub n's are positive in the first place. So if a sub n squared converges, then the limit as n goes to infinity of a sub n must equal 0. It has to be going to 0 in the first place. And a sub n squared has to be doing so sufficiently fast, but that doesn't really mean anything. And apart from still hurting, it's not actually too bad. The burn is almost gone. So that's good. I have been shoving crackers and cheese in my mouth this whole time, so that helps. Okay. Alternating series will converge provided that the terms a sub n decrease monotonically with a limit of 0. That's it. So, yes, we have that. So the limit of 0 is going to come into play from the series a sub n squared converging. So since it converges at all, we know that the limit of the series a sub n must be 0 as n goes to infinity. So that's going to apply whether we're doing a sub n squared or a sub n. Doesn't much matter. But we need this limit of a sub n to be equal to 0 regardless. And I guess technically this is the limit as n goes to infinity of a sub n squared being equal to 0, but that's going to imply that the limit as n goes to infinity of a sub n is also going to be 0. And this says we're monotonically decreasing. So this is also going to work. 2 is going to work because of direct comparison series, or direct series comparison. And 3 is going to work by alternating series. And 1 fails because we can find a counterexample like p series k equals 1, or k raised to the 1.1 power. Right? If we take the square root of that particular p series, it will not converge. So yeah, it's going to be A, B, C, D, E. These are going to be the same predictable ones that we had in weeks before. At least I think so. 1 and 2 only. 1 and 3 only. 2 only. 2 and 3 only. 3 only. She got it wrong. I'm not telling her. This was 20 some odd years ago, so. Nope, she didn't get it wrong. She got it right. There's a bunch of just hash marks that go through, like crossing it out. I thought D was crossed out also, but it's sort of like going like that and then coming all the way across. And there's nothing on C. So. Never mind, she got it right. All right, 45. If x is on the open interval from -1 to 1, then sum as n goes from 1 to infinity of n x to the 2n equals what? BV sense? About to take your trig final tomorrow. Do you know any good websites that would have practice questions? If you're just looking for practice questions for stuff, I mean, Khan Academy and Purple Math and a bunch of these other sites might be pretty good. So, whereas I am doing Calc 2, my main priority is just helping people out. And trig happens to be one of my specialties because I was the coordinator for my school's trig course for basically 10 years. So if you have any particular questions, let me know. I do tend to teach the teach to your understanding of stuff rather than necessarily just giving a bunch of questions and answers or what have you. So if that might not be helpful, I can attempt to abbreviate it. But definitely, if you have any questions, let me know, and I will be happy to help out. Yeah, proving identities was one of those that was kind of a necessary evil, mostly because we were just the goal, right? The goal is for us to make sure that you can perform some mental gymnastics to say, like, I understand how to get from point A to point B, or I can play with stuff a little bit. And when you're talking about trig, when you're talking about any identities and proofs, I tend to think of it like each of the sides have a particular like energy level that they're working with. So something like no, 1 plus square thing, 2. I think this was it. this was, if I copied it correctly off the top of my head, this was one of my favorite questions because every single semester students would teach me something new. And yes, they would teach me something new. Every class would attempt something slightly different, and after about 3 or 4 years, it ended up being slightly repetitive in that most of the time they would repeat one of the previous things. Yeah, sure, go for it. Oh yeah, no worries. So looking at 45, this was within the radius of convergence, with x being between -1 and +1, because no matter what n is here, with a 2n as an exponent, we're always going to end up with a smaller and smaller and smaller value for x as n gets bigger. So man, that's mean. I imagine this is a essentially Taylor series question where it's like, okay, well, what's this going to be? What are you doing here? This is not nice. So, and going from 1 to infinity, this would be n. This could be x to the 2n plus 1. I don't like that one so much, but it'd do. No, okay, so since we're only really dealing with things that are like 1 minus x, 1 minus x squared, and then the squared terms on the outside. Okay, what we've got then is that this is going to be x squared parentheses to the n. So that is a square that's on the inside of the function. I do not like this. Okay, this, because they're all positive, this would be 1 over 1 minus x is equal to 1 plus x squared plus dot dot dot. So 1 over 1 minus parentheses x squared, or not parentheses, but whatever. It's 1 plus x squared plus x to the fourth plus dot dot dot. So this would be n is 1 to infinity of x squared to the n. Okay, we'll come back to that in a sec. Right. Make tangent to the fourth theta into sine over cosine and secant into 1 over cosine. Sounds great. Right, so then this side we've got sine to the fourth theta minus 1 all over cosine of the fourth theta. Cool. And yeah, I'd recommend leaving the right-hand side as it is until we need it, unless you feel like changing it up now. That's fine too. See, okay, so this is, again, this is sort of like why I like this particular question, is like, basically you can move in any direction and you'll eventually get something. So I will show you at least 4 different ways to do this, probably. Would sine of the fourth theta over cosine of the fourth theta be equal to 2 tangent squared theta? So because you have this 1 that's here, right, this is 1 over 1. This 1 is not 1. It is 1 over cosine of the fourth theta. Right, so it still retains this structure. So you're not going to be able to just, like, eliminate it, unfortunately. Now, however, again, there are multiple ways of actually doing this. So you've got one where, okay, we're going to take the left-hand side, combine it into a single fraction. And at this point, you could either, because you've done that on the left, you might also want to do it on the right. Right? Tangent squared can become 1 plus 2 times sine squared over, sine squared theta over cosine squared theta. And then because we're doing this whole fraction thing, right? Let's make it common denominators. Sure. So the 1 is going to become cosine squared theta over cosine squared theta. And then the rest of it is this plus 2 sine squared theta over cosine squared theta, which was down there. So again, we've got multiple ways to go. So again, it sort of depends on how you like to move in this. When I see something with an even power minus something else with an even power, in this case, right, 1 is just something to the 0, or anything to the 0 except 0 itself, and sine to the fourth of theta is very nicely an even power. This is telling me that this thing can be of the form a squared minus b squared, which is a plus b times a minus b. So if you want to, again, you don't have to, but if you want to, you could split that up as sine squared theta plus 1 times sine squared theta minus 1. Does it help in the immediate short term? No, not really, but it can help you figure out how to work with stuff. And if you can get a like term on the opposite side, you can cancel them out. Again, does it work? Maybe not in this exact case. That's fine. On the right-hand side, again, we could do some stuff. We could do multiple things. In this case, my immediate reaction is we have a cosine squared plus a sine squared. Now we have multiple, right? We have 2 sine squareds, but we could split that up as a cosine squared theta plus sine squared theta plus sine squared theta, which means that cosine squared theta plus sine squared theta can be 1 by the Pythagorean theorem. And then now we've got 1 plus sine squared theta. And now that's familiar, because over here we had a sine squared theta plus 1 sine squared theta minus 1. Over here, now we've got a 1 plus sine squared theta. Factoring and finding perfect square. Yeah. So over here we get cosine squared theta in the denominator. And again, now we've got this here and this here, which can divide out from both sides to get us 1 left over. So now on the left, we've got a sine squared theta minus 1 over cosine to the fourth theta, which is equal to 1 over cosine squared theta. And then we could say, I don't really like having cosine to the fourth here. So if I multiply both sides, by cosine to the fourth theta, hey, come on, there we go. Then on the left, again, this is going to divide out nicely. And on the right, 2 of them will divide out nicely. And so now we get sine squared theta minus 1 is equal to cosine squared theta. I think that looks familiar. Although, wait a minute, it is ever so slightly off. You know what happened? That might have been a 1 minus 2 tangent squared theta. Well, at any rate, you'd look at this and you could say, hey, this is not an identity. Because in this case, what we have is that sine squared theta is equal to cosine squared theta plus 1, which is not an identity. Right, it would have to be 1 minus sine squared theta. So this was off by a negative. You know what it was? It was this. It was the term all the way at the top. It was supposed to be secant to the fourth minus tangent to the fourth. So just swapped around. So I was technically wrong here. Right? It should have been secant to the fourth theta minus tangent to the fourth theta is equal to 1 plus 2 tangent squared theta. So use this as a template because, again, you could do this one in, like I said, at least 4 different ways that are all, kind of independent of each other. And it works out great if you can, figure out how to just tweak stuff around. Let's see. One of my students also said, I would prefer to move this over to the other side. I was like, all right, that's pretty bold. Secant to the fourth of theta is equal to 1 plus 2 tangent squared theta plus tangent to the fourth of theta. Okay, where are we going from here? And he said, that's a perfect square trinomial. That's 1 plus tangent squared is equal to secant to the fourth of theta. And I said, absolutely, 100%, yes it is. And then what happens from here, he said he wanted to make this, take the square root of both sides, because everything on the inside of both of these is going to be positive, both before the square root and after the square root. So secant squared theta is equal to 1 plus tangent squared theta. These are always positive. So we don't have to worry about pluses and minuses. We don't have to worry about absolute values or anything like that. And then he looked at this and he said, secant squared theta plus 1 plus tangent squared, or secant squared theta is equal to 1 plus tangent squared theta is an identity. And I said, okay, so either we just immediately say, yes, it's an identity, or we go to the easier one. So I did recommend a lot of my students go and take this and say, okay, how is an identity? That's 1 over cosine squared theta is equal to 1 plus sine squared theta over cosine squared theta. Multiply by cosine squared theta all the way through, and nope. 1 equals, this is cosine squared theta plus sine squared theta. So this was completely inventive. It took me by surprise when he did it. I was like, oh, yeah, that works. Cool. This was like 4 years into teaching it. Student came up with something brand new to me. I was like, all right, cool. It's not what I was expecting at all. But yeah, like I said, there's all sorts. So here, another student took it immediately as difference of squares. Said that this is going to be secant squared theta. Secant squared theta plus tangent squared theta multiplied by secant squared theta minus tangent squared theta is equal to all that stuff up there. And then here, we know from the bottom down there that if we put the tangent squared over with the secant squared, right, it'd be secant squared theta minus tangent squared theta is equal to 1. So that one is just equal to 1. So secant squared theta plus tangent squared theta is equal to 1 plus 2 tangent squared theta. And then again, where do we go from here? We could take secant and use the exact same thing from down there. So 1 plus tangent squared theta plus tangent squared theta is equal to 1 plus 2 tangent squared theta. And I don't think we need to belabor that point. That's pretty obvious. So yeah, this particular one has a very large number. Like this is a what would be called a rich problem, where you could come at it from any number of different ways, and it teaches you something different every time that you do a different way, or it's testing a different skill. I would say you're not wrong. And dare I say, Zach might say the same thing too. These are many of our mathy type friends who are here on Twitch. And at various points during the week may do a math stream of some kind or another. So Slim from Academy of Useless Ideas, Dr. Gold from Actual Education, Don Factorial, E.N. Stuckey, Zach from E to the 2i Pi, Meriwether Remark, Penn Center, Phobostream, Physics and Depression, Talus Teaches, and the Tutor Wizard all, like I said, do some sort of math at some point or another. People like Physics and Depression and Dr. Gold from Actual Education are more toward physics, as one might expect from Physics and Depression. But they do take like requests to do math as well as do mathy stuff within their physics. Hated doing them in high school? Yeah. So did I. Mm-hmm. Yeah, forgetting everything is always rough. I could appreciate it though, because I had one of my best students who then I believe went on to also become, at the very least, a tutor slash like a developmental instructor. Was in my differential equations class in, gosh, probably 2016. And he got called out on active deployment while he was in my class. And I'm like, just like one more month and it wouldn't have been a problem. But he got all of his work done on the boat. Whenever they came up for, shore leave or resupply or whatever, his stuff would be in a packet of information to be sent back, and so they would, upload things onto our Canvas course and do as much work as he could, and then they'd go back down because he was in a sub. No, I mean, even if he was on a destroyer or whatever, he wouldn't be able to have internet all the time. So, yeah, every time they came back out for whatever, you'd be able to send some stuff onto the Canvas course and then go back out. And then I'm like, well, I mean, he's not going to be able to take the final until he gets back. But he finally did get back like the week before school started again. And he was like, can I take my final? I'm like, absolutely, let's go. Yeah, Canvas got hacked by some ransomware company. By some ransomware pirates. And they were like, yep, we're going to just demand that instructors send us money. So tell them that we're demanding money. I'm just like, man, talk about low-hanging fruit. No service yet. Yeah. 4 months of absolute boredom followed by 10 minutes of sheer terror. Uh, Whatever it might be, doesn't have to be combat. There's always something that sends somebody into a tizzy. Oh, Interstellar, yeah. Such a great movie. I always had I had a recurring nightmare from when I was like 3-ish until, I mean, like, I only had it a couple of times, but it stuck with me. Probably until I was like 10, where I'd be at the beach and I'd be laying on a particular, like, blanket that I had as a baby. And then, like, I would see just a wall of water coming. So, Miller's Planet was a little traumatizing for me. De Moivre's theorem to find powers of roots in complex numbers. Yep. So the basic idea, right? If you just want, I need numbers, throw the numbers in here and do that. Then what you've got is this cosine theta plus I sine theta is being raised to some nth power. And, oh, R. I need an R. R to the n times cosine n theta plus I sine n theta. Alright, that's the crux of de Moivre's theorem. Now, you do come at this from a slightly different angle in that, but usually we're saying that this is going to be a plus bi is being raised to the nth power. Right, but then we take this and we say, okay, a plus bi is equal to r cosine theta plus I r sine theta. Right, so how does this work? Well, Euler's formula, and if you look at Zach's username, right, e to the 2I pi is equal to 1 is Zach's username. Now, why is that the case? Well, that's because here this is e to the I theta, where theta is equal to 2 pi. So we could also use this as a template for how to convert from rectangular form into polar form. Now, if you're comfortable with that, then awesome. But the idea is that a plus bi can also be rewritten as r times e to the I theta. So how do we do that? Again, this is going to be the any number of ways of figuring it out. A plus bi, you go like this, you get that, get the right angle, you get that. You've got A, you've got B. Here you've got your theta, here you've got your r. So r squared is equal to a squared plus b squared. Theta, there's a number of different ways, but usually inverse tangent of b over a. And typically you don't want to use something that you just calculated in order to get the next step unless you absolutely have to do it. So don't calculate r squared and then calculate the inverse sine of b over r. Just because you might end up messing up r, in which case you've also now messed up the angle. Right. Ads are going to start here, so we will see you in 3 minutes. Thank you everybody for coming, and be right back. Okay. So the reason that De Moivre's theorem works, or at least one of the easiest illustrations for it, is that we can use this polar form right here, which uses the exponential. So if I want 2 plus... I guess we'll do an easy one, right? 2 plus 2i converted to polar, and specifically converted into exponential polar. Right, theta is going to be equal to pi over 4. Since it's both the same x and y coordinate, it's 45 degrees. Since they're both positive, it's going to be the first quadrant. So 45 degrees in the first quadrant is pi over 4. And then we look at r, and we say that this is going to be the square root of 2 squared plus 2 squared. So 8, so that's going to be 2 root 2. Also, if you know that it's a 45-degree angle, you could say it's going to be the x coordinate or the y coordinate, because it's the same, times the square root of 2 to get you the diagonal. All of it's good. So, with all this taken together, that's going to make it 2 root 2e to the I times pi over 4. Okay, then if we want to take this and say that this is going to the 10th power or something like that, well, how does that work in exponential form? Well, 2 root 2 is going to get raised to the 10th because this is something that's multiplied and then being raised to a power. So 2 root 2 to the 10th times, parentheses, e to the I pi over 4 to the 10th, right? Each individual part's going to get raised to the 10th power. What does that do here? Well, that's going to take the r that we had and just raise it to that power. So a few different ways we could have done it. I could have also said that this, instead of being 2 root 2, was the square root of 8, or 8 to the 1/2 power. And so raising that to the 10th power is going to multiply the exponents together. So 8 to the 10 over 2, or 8 to the 5th, or 2 to the 15th. Number of different ways you could do it. It all works. Okay, and then the other one, we're going to multiply the exponents together, right? A power being raised to another power. So e to the I times 10 pi on 4, which is e to the I 5 pi on 2, which is going to be coterminal with e to the I times 5 pi on 2. We could subtract 2 pi, which is 4 pi on 2, so that's going to get us just pi on 2. Now, it did give it to us in rectangular form, so probably it wants the answer in rectangular form as well. So at this point, we need to know what 2 to the 15th is. I think that's 32,000, is it? 32,768. Yep. So 32,768 times, and here e to the I theta is going to be, again, cosine of theta, pi over 2, plus I sine theta, pi over 2. which is pi over 2. Right? Cosine of pi over 2 is 0. Sine of pi over 2 is 1. That's 1 times I. So this is going to be 32,768 I. Okay. So that works really well for how to discuss what happens with the polar form of numbers, complex numbers, for de Moivre's theorem. What we're doing is we're raising our radius to whatever power it was that we were raising our original complex number to. Right? Why? Because it's a multiplied portion. R times all the other stuff. And so the n there, your power, just raises r, makes it r to the n. Easy enough. And then this cosine theta plus I sine theta, how does the n get put into the arguments? That's just like bonkers, right? Why should it be n theta for both our cosine and our sine? Well, because again, if you look at it in the exponential form, this is just the same as what we do with r. We raised that thing to the 10th power over here, or the nth power up in the general formula. And so if we raise that exponential thing to the nth power, it's going to make I times n theta. And now n theta is our new angle. So once we get that, we have our r to the n times cosine of n theta plus I sine n theta. Yeah, knowing the connection to the exponential form just makes this whole process so much easier. And it's not a mystery anymore. Like, why does this happen? That's just crazy. It's a little bit more obvious to be like, well, yeah, I mean, it's just an exponential. So you're raising your radius, and you are I guess no, I don't want to say that. Yeah, you're raising your radius, and you're going to multiply your angles by that n value, whatever it is. Now, the other way was what I was going to say. When you do, right, cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2, when you're doing the multiplication of two different numbers, and again, here you get R1 and here you have R2. No, don't do that. And here you have R2. Here you have R2. Right, when you're trying to combine these two things, we're doing the same basic idea as de Moivre's theorem. Again, if you look at it in exponential form, it's R1 e to the I theta 1 times R2 e to the I theta 2. Okay, what happens? Well, you multiply your moduli. R1 and R2 just get multiplied to the front because of course they do. They're multiplied terms, and they're more similar, so you bring them together over there. And then what happens over with your other stuff? Well, it's e to the I theta 1 times e to the I theta 2. Well, those have like bases, so you can multiply them together. So R1, R2 times e to the I parentheses, because now you're adding your exponents. Theta 1 plus theta 2. So you multiply your moduli and you add your angles. When you do de Moivre's theorem, you're just doing it a bunch of times with the same numbers. right? What's raising something to a power? It's multiplying stuff over and over and over again. What's multiplication? Well, multiplication is just when you add a bunch of stuff to itself over and over and over again. Didn't learn anything about E in class? Yeah. So the connection is nice. It's not necessary, but it is definitely nice. And that's the that's the Euler's form, which you don't really learn about until Calc. Usually even Calc 2, but e to the I theta is equal to our cosine of theta plus I sine of theta. It's a really helpful property to know, and it leads to one of the most absolute beautiful things in the entire world, which is e to the I pi plus 1 equals 0. This is Euler's identity, which uses the 5 most important constants in mathematics, all in the same place. Right, 0 and 1, our respectively additive and multiplicative identities. E, which is our natural base. I, which is complex number square root of -1, and then pi, which has to do with circles and angles and stuff like that. So, again, this particular thing just makes everything a lot easier. But if you don't know it, it's not a big deal. Evidently, your teacher doesn't think it's necessary. Mm-hmm. Awesome. How about that one? You may not have to do this, right? This may not technically be part of your exam, but there's a pretty good chance. And in fact, let me do negative just to be slightly more of a pain in the ass. No, not at all. So this one is just solve the equation. One of my favorite things to do with this is just make a picture of it. You can, in fact, solve for cosine of 2 theta as an identity and say like, okay, cosine of 2 theta is equal to what? And break it down and make it a little bit easier for you. However, there's also something else that you could do, which is, if you remember, right, where are we on the unit circle? Well, cosine has to do with your x values. Well, not necessarily. If you have a cosine, then you're saying that the x value, right, the horizontal value of your argument is going to be negative. The cosine of, now don't worry about the precise nature of what you're looking for at this exact moment. We'll get to it. This is going to be 1/2. Which means the angles we're looking for are here and here. So that one and that one. Right. So again, cosine is x value. And the line that I drew in here is x equals negative 1/2. Right? Where this is -1, this is 0, this is 1. And up and down as well, right? Zeros and ones. So here, x is equal to 1/2, negative 1/2, gets us this vertical line. And then where does it intersect the circle? It intersects the circle up here and down there. Down there. Where are those? I mean, if you know your identities, if you know your trig, right, this is going to be a 60-degree reference angle. Right, in quadrant 2 and in quadrant 3 is going to get us, okay, 60 degree is pi over 3. In quadrant 2 means that we're doing a pi minus pi over 3, and in quadrant 3 means we're doing a pi plus pi over 3. And yeah, it would be easier if you know it just offhand, obviously. So yeah, 2 pi on 3 here and 4 pi on 3 here. But wait, there's more, because this is not the answer to your question. Right? This is not the answer to what angles are going to get me negative 1/2 when I take the cosine. Or rather, that is precisely the question that I'm answering here. These two angles will only get you the x values of the angles whose x values will get you negative 1/2. But that's not what we're looking for. We're looking for what angle, when you double it, will end up getting you an x value of negative 1/2. So, the issue here is that since this is 2 theta, we need to look at what values of 2 theta are we going to get, potentially, for all of this. For 2 theta, we should be looking for values that are between twice our original 0 to 2 pi. So from 0 up to 4 pi exclusive, we're going to look for all 4 angles that could get this. Because when we do this, you're going to see that, oh my goodness, yeah, it's going to end up, we're going to end up with additional angles. So how do we then do it? Right, we say we could get 2 pi on 3 or 4 pi on 3. Or we could add an additional 2 pi to those. Because again, this is 2 theta. Right, so 2 theta 1, 2 theta 2, 2 theta 3, and 2 theta 4 subscripts. These are all the 4 possible values that we could get here. So now we say, okay, if we then add the 2 pi onto these, we end up with 6 is 8 pi on 3 and 10 pi on 3. So with that, 2 theta could be any of the following: 2 pi on 3, 4 pi on 3, 8 pi on 3, 10 pi on 3. But then that's 2 theta. So divide by 2, and theta is going to be pi on 3, 2 pi on 3, 4 pi on 3, and 5 pi on 3. And now you can see that these are within 0 to 2 pi. Did one like that with x equals 12, made a table using r equals 12 over cosine theta, going up 30 degrees every point. Using polar. Like to graph polar graphs? Or to do this specifically? Not necessarily. So with what you're saying, it looks like what you're saying is r of theta as a function is going to be 12 over cosine theta. You look for all the values of theta and r, and then when you graph, close enough, you might end up with something that looks like this. Beautiful. I guess I would maybe caution, like, what is it that the question is asking and what is it that the question's looking for? So the previous one was solve this equation. This one is, we now have an equation with 2 variables, so we can't solve it, but you can throw in a bunch of numbers and see what happens. So the relationship that exists between cosine theta, or just theta, and r of theta, or just r, is going to be this like inverse relationship, which then causes it to do some funky stuff once you start getting in there. That's actually not what this looks like, but whatever, it's fine. Yeah, okay. That's just actually a vertical line. Where we can't actually get particular values. Okay, cool. Not on Desmos anyway. Practice question during the lecture. Simple equation just using polar x equals 12. So therefore do this. I guess. Yeah, I mean, me personally, I much prefer going with the analytic method, just so that you can definitely see what all the answers are and how all those answers exist. In theory, you could go this other way and say, okay, where are we going to cross this line? Where is this function going to cross this line? And try to find all the different ways of doing it. It's fine. It is, I guess, sort of what I was doing with this, right? Or if we go the other way, we could just literally say, what's the cosine of x? And what is y equals negative 1/2? Whoops, 2x. And where does it cross between? Here we go from x-axis, negative 0.5 out to 2 pi plus 1. Okay, and then the y-axis will go from negative 1.5 to 1.5. Right, so then increase the contrast. So where between 6.28, so that's roughly speaking here, and 0, do we then cross the line, or cross our two coordinates? So here, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Which, right, that was the set of values that we had back over here. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Like I said, I much prefer the analytic method of going through and making sure that we have every single thing. It is definitely a good idea to check with the graph or even start your understanding with the graph itself. Yeah. Richie, how's it going? We're looking at some trigonometry. So, BB Clance came in and let me know if that's wrong. and wanted to know some information about some trig stuff. And I've been teaching. Okay, I've been teaching trig for roughly, well, teaching trig for roughly 15 of the last 17 years, and have been the coordinator at my community college that I left about 2 years ago. For 10 of those years. So, I believe after 3 or 4 years, I did a report. Thank you for the follow. Yep. Have a good eat, have a good sleep, and then have a good test. So good luck with that. You'll do great, I'm sure. Thank you for the follow, Rishi. So, after about 4 or 5 years of being at this college, I came to realize that I had become the person who had taught the trigonometric class the most ever. And it didn't take me that long to do it either. But they just kept giving me this class every single semester, and I kept requesting it over and over and over again. And yeah, like I said, I ended up being the person who taught it the most out of everybody in the history of the college, going back as far as we had data. I was like, all right, well, I guess I'm the expert now. Rishi, if you have any questions, let me know, or if you have any particular subjects you want to talk about, let me know, and I'll see what we can do. If anybody else has any other questions, feel free to do so. And other than that, I have been working on cracking the GRE. It's the Graduate Record Exam. I did this back in 2004. This second edition book from the Princeton Review is from 2002, so it is 24 years old. This book is old enough to drink in the United States. And yeah, this is the book, the exact same book that my spouse and I both used to review for the GRE before we actually took it. Mechanical engineering, nice. All right. Right there. Okay. So this is Calc 2 stuff. There's a bunch of infinite series, and we're talking about Taylor series in particular. So where were we? We said that we've got n times x to the 2n. X to the 2n can be rewritten as x squared to the n, which then means that 1 over 1 minus x can be rewritten as a Taylor series like this, or it can be rewritten with the argument being changed from just x to now x squared. When we do that, we then get 1 over 1 minus x squared is equal to 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th, etc. Where it's basically just now even exponents on x. Explain what are limits and why do we need it? Yeah, so I was in Zach's chat yesterday. Right, I saw you ask the first time. So generally speaking, right? If we have a particular function and we want to know what its limit is as we approach a particular value, so a. Yeah, no worries. And getting me to explain it is going to be ever so slightly from how Zach explained it. And if you can get multiple other people to also explain it, there's a good chance that you're going to kind of like get closer and closer to understanding from multiple different perspectives and multiple directions. So it's a good way to do it. I know Zach is usually very precise with his language, and I am far less precise, but usually get people with less experience tend to understand me fairly well, so we'll see. Okay. So when we're talking about just like some function, I'm just going to draw a line for now. Let's say that this is, something like this, and we're going to zoom in on this little section which looks kind of flat. Right? So we're just going to zoom in. So we see this little point that's kind of like in the middle here. And we'll call that a comma f at a. So we got this point here. It's at a comma f at a. Now what we want to do when we're talking about the limit is not talk about that point. So for instance, what exactly is going on around this point? What are they all pointing to? Right? And what do I mean by pointing to? Well, if you just start selecting individual points which are on this function and which are close and getting closer to a, that x value of a, right? We're going to keep getting closer and closer and closer and closer and closer, never actually reaching it, but getting closer and closer to it. And every time we get closer, we point, like what was our direction of travel? How do we move from here to there? Right? We do the same thing on the other side. So this is here, and then we get more points and more points and more points. Again, really, really close to A, but not actually touching A itself. This is what's known as a limit. Right? So what we're doing is we're saying, if we just start looking at all the points that are around this particular point, then what is it that we actually are pointing to? We could do this in a number of different ways, but the most important and powerful reason to do this is if we have a function that's actually missing a point. Let's say just x equals 2, right? So if this point is undefined at x equals 2, what we have here, again, if we zoom in, is a number of points that are real close to this point. We keep getting closer and closer and closer to it. And on this side, we keep getting closer and closer and closer and closer and closer to it. We never actually reach that point. The x value at 2 doesn't exist in this function. Right? So f at 2 is undefined. I'll give you an example. If we have from pre-calculus, one that looks like minus x minus 2 divided by, and this is f at x is x minus 2 divided by x squared minus 4. All right, this is x minus 2 over x plus 2, x minus 2. All right, x squared minus 4 breaks into those two pieces. Now, if I just go in here and I take x minus 2 and I cross them out here and say that, what do we get, right? We're just going to get 1 over x plus 2. Well, this is not the same function as this. Right? 1 over x plus 2 is not the same function as x minus 2 over x squared minus 4. Because if we tried to plug in... yeah, that's right. Right? If we tried to plug in x equals 2 into this thing, we get 0 over 0. We're not allowed to do that. Right? 0 over 0 is undefined. Whereas over here, if we plug in x equals 2, we get this value of 1/4. This is very much defined. So these are not the same function. If we want them to be the same function, then we have to add on to the end. And we have to say, okay, we're not allowed to do this. We have to say that x cannot be 2. And then we can come through and say, aha, now they're equivalent. This f over here, x minus 2 over x squared minus 4, is now the same as 1 over x plus 2 as long as x is never 2. Okay, so does that make sense so far? Might be a little weird, but okay. Now, something I will often do is take the location where it is defined, where we say, okay, f star of x is just 1 over x plus 2. So f star at 2 is 1/4. Then I take this and I say, now I can at least label the whole. And it is what we call removable discontinuity. Also just known as a whole. Okay. This means that the limit as x approaches 2 of our function f of x is going to be equal to 1/4. Yes, so if you're looking at it from a more calculus perspective, that's where you'd go with that. So they're really looking at it in terms of like trying to find the ratio of slopes and saying that, we're trying to get, and if you're trying to do it from a calculus perspective, then that's perfect. What we're trying to do for that is say that we've got a curve for which we have 2 points. We'll call this x f at x, and we'll call this one x plus h, f at x plus h. Right, the distance going up and down, right, delta y, is equal to the distance between their y values. So f at x plus h minus f at x. Sorry. The change in x is going to be the difference in their x values, done in the same way. So x plus h came first in the other one, so it's got to come first in this one. So x plus h minus x, which is just h in this case. So delta x is h. So if we want the slope, this is delta y over delta x, which is f at x plus h minus f at x over, and we could say just h. Okay, so that's just generally how we talk about slope. Then, if you want to get the much more fun part, the calculus part, what we say is, and this is what Newton did and Leibniz did back in the 1600s, they said, what would happen if we took that point and started like moving it in closer and closer and closer to the other one? So as we do this, we're going to get different values for the slope. And they're going to start getting closer and closer and closer to the true value of the slope of the... don't do that. We're going to get closer and closer and closer to the slope value of this line, right? What's this line? Well, this line is what we call the tangent. Tangent line to the curve. It only touches it once. It's very specifically at this particular angle that's going to end up hitting that curve only once. And if it's like a weird curve and it keeps going up and down and up and down and up and down and bonking into your tangent line a bunch, just zoom in, right? Until you're locally looking at something that's still curved, but like doesn't have a lot of other crazy stuff in there. So when you look at it locally, you're seeing it as this is just going to touch it once. And like, if you were to think about like a car that's kind of drifting around a corner, or a ice skater who like has fallen over, stuff like that, right? You're terrible. Anyway, what you're looking at is like the direction of travel. So currently, that particle is headed in that particular direction. is sliding that way. But then the overall trend is that it was going much more vertical, and now it's starting to curve out further and further that way. Okay, so all of these other green ones here were called secant lines because they intersect the curve more than once. So they're intersecting the curve at our green point, and then they're also intersecting the curve at all these pink points, salmon points up there. Okay, so our tangent line has a slope of, again, we would only have one point, x comma f at x. Well, we can't do that because we need 2 points to define a line. And if they're the same point, we just get 0 on 0, which doesn't work for us. So what we're doing is we're saying, okay, we're not going to find the slope of the line at a single point. What we're going to do is sort of a little bit of, I hate to say trickery, but it does tend to look like it. So what we're going to do is we're going to take the limit as h starts going to 0. So that distance that we're traveling in the x direction is going to get closer and closer and closer to 0 of our delta y over delta x. Okay, which is the same as our limit as h goes to 0 of f at x plus h minus f at x all over h. Right? So if we just tried to directly plug in h as 0, so here we would get f at x plus 0 minus f at x over 0. So f of x minus f of x over 0 is 0 over 0, which is undefined again. So we can't do that. But instead, what we do is we say, okay, if there's a way, what we're going to do is we're going to find some way to get an h out on top, multiplied by a bunch of stuff, divide by h, and then the h's go away, and then we're left with this nice bit over here, which is going to get us an answer. We just can't just do it, but if we wanted to, for instance, find the tangent slope of y equals x squared. At x equals 2. All right, so we've got our nice parabola like this. We're somewhere up here. This is 2 comma 4, right? That's what we want. And now we want the tangent slope. So what is the slope of the line that connects right here? That looks actually very good. So what are we going to do? Well, we're going to pick a different point on the parabola, and then again label that as, well, again, we're going to take our x value, which is 2. We're going to add some unknown h to it in the x direction, and then this is going to get us x squared. So our x coordinate in this case is 2 plus h. So this is going to be 2 plus h parentheses squared. So let's set up the slope formula. This is the limit as h goes to 0. Limit as h goes to 0 of the distance in the y values is going to be 2 plus h parentheses squared minus 4 divided by h. I was going to say the distance between our x values, but we already know what that is, right? 2 plus h minus 2, just h, right? And with a little bit of work, we just say, okay, this is the limit as h goes to 0. This stuff, when we multiply this all out, oops, we end up with 4 plus 4h plus h squared minus 4 all on h. And you'll notice, right, our 4 and our negative 4 are going to subtract out. So that's 0, that's fine. And then we get here 4h plus h squared. Both of those have an h, pull that out. Then we get 4 plus h all over h. These two h's are now multiplied, so divide them out. And now we get the limit as h goes to 0 of 4 plus h, which is just going to be, now we can plug it in. Just plug it in. We get a finite number. It's going to be 4. So at x equals 2, we have a slope of 4. Right? So the slope of the tangent line to the parabola y equals x squared at x equals 2 is going to be 4. So here, again, what we were doing is we were saying we're going to have two separate points, but this point up here, the one that's up higher, is going to get slid down as close to as we can, where h is going to be approximately a 0 distance. So we're going to keep thinking about it as a teeny tiny bit, an infinitesimally small amount of a deviation away from 2, 4. Now we could do all sorts of stuff with this as we go on further. One of the favorites ends up being for integration. If I want to find out what the area under this curve is, between these 2 points. So I want to know what the area of all this is. I could make a bad approximation. By taking a bunch of points and just drawing, those are totally rectangles. Don't listen to what anybody else says. Right? I could split this thing up into rectangles. And then I could say, give me the base and give me the height of all of these rectangles. And then when we multiply all those bases and heights together, then add them all up, we get a bad approximation of the area of this thing. Okay, this is when n, number of rectangles, is 1, 2, 3, 4, 5. Okay, but what if I did instead n equals 20? So that says that in the middle, and then at each of the quarter points of those rectangles, I'm going to find a new point of this function here, and here, and here, and here, and each of those here, and 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 here. Do, 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 do. And now I draw rectangles from each of those. Etc. Right? Just if we pretend I'm just going to, yes, I'm totally going to do them all. If I do each of those, now my approximation is much closer to the true value, because all I'm missing now is these little triangles in here, these little tiny corners. And that is nowhere near as much of a problem as these big triangles were in here that I was missing before. This is going to be this is going to be much bigger than if I did something, which means I can't just go forward again. You think I would know that by now, right? That is much bigger of a gap than these triangles are in here, even when summed up. Okay. So we do that all the way across the entire function. And the more rectangles we have, the better an approximation we're going to get. So what we do is we then say, give me the limit as n goes to infinity. As all of our rectangles become infinitesimally small in width, then we're going to get an infinite number of rectangles inside of this curve, and then we're going to be able to find the true value of the area under this curve. N cannot actually be infinity, right? Because the delta x down here, the distance between all these, is our b minus a divided by n. So if n is infinitely large, like you can't actually calculate what x is. We can say that in the limit, as n goes to infinity, delta x is going to go to 0. But it's never going to actually be 0. It can't. Doesn't make any sense. If delta x were exactly 0, then we would never go anywhere. All of our widths would be equal to 0. And so all of our areas would be equal to 0. And that's an absurd thing for me to say, right? Because that's our goal, is we're trying to find the area under the curve. So limits really are not saying what is this thing, but rather what is the trend? What is going on as we get close to whatever this thing says it is? So as n gets really, really, really big, what's happening to the overall picture? We're getting a better and better and better approximation of the area under the curve. If n were to be so large as to be infinite, then it would end up getting us the actual area under the curve. Similarly, back up here with what we were saying before about the tangent slopes, right? If we just take this one point, x comma f at x, and try to create a line, we can't do it. But if we create this limit, which allows our h, the horizontal distance, to get really, really close together as if it were 0, then we can start thinking about, okay, as if it were 0, what would that do to the structure? That gives us, in this case, the ability to knock out these h's and create something with meaning. So instead of 0 divided by 0, we now have 4 plus h is the value of this slope. All right. I hope that helps. I also hope it's somewhat easy to understand. All right, and with that, we're going to head over to one of our other academic type streamers. Well, thank you very much. And definitely ask more questions of either myself or other people to try to figure out, a better way to understand it. Okay, let's go say hi to Rhacodactylus, who is currently looking at the relationship between science and pseudoscience. Reiko is somebody who does conspiracy theories, and I think that was his PhD, was trying to figure out why conspiracy theories exist and what kind of structures they have just altogether. So I hope you have a nice evening. We'll be back tomorrow for TTRPG writing, and then we'll be back Friday for Baldur's Gate, if all things go well. So we'll see you then, and next Monday and Wednesday for mathy stuff, just in case you're only here for that. But hope you all have a good rest of your week, rest of your night, whatever you got, and stay safe out there. Good night, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko.